This is just a quick video on the magnetic field generated by a flat loop. So the assumption here is that the length of this thing, in other words, this 1.6 centimeter dimension, is much less than the width of it, the diameter 20.6 centimeters. So this one qualifies as being flat enough to be flat. In this case, the magnetic field at the center is given by this formula, N times mu naught I over 2I, where the capital N is the number of turns in the loop, mu naught is the permeability of free space, and R is the radius of the loop. So that 2R down there could simply be replaced with a D for the diameter, which is what I'm going to do in the video. So with any luck, I'll be able to actually test these in the lab very soon and hopefully attach that to this video. The coils in my lab have 200 turns. The average diameter is 20.6 centimeters, and the length of the loop, again, is 1.6 centimeters. And we're going to test these with 1 amp of current running through them, and hopefully put a Hall probe at the center point of the loop and obtain a magnetic field that agrees with what we calculate first. So in part A, I'm asked for the direction of the magnetic field at the center of the loop, and I use the Ampere's law right hand rule for this. So I put my thumb in the direction of current, curl the fingers of my right hand around, and that's the way the magnetic field is looping around the wires. That means the magnetic field is pointing up inside the plane of the loop and down outside of the plane of the loop. Just qualitatively, the loop lines look something like this. You can test at several points. Use the right hand rule with your thumb pointing into the page right over here, and your fingers will curl around in that direction of field. And by symmetry, right at the center, your magnetic field is going to be pointing straight up. So we'll want to take our Hall probe and put it perpendicular to a field that we expect to be right along the same symmetry axis as the loop itself. Now I want to get the field magnitude at the center, and this is just a matter of plugging into the formula. N is the number of turns in the coil, that's 200. There's mu naught, there's the current, 1 amp over twice the radius. Well, I have the diameter already, so I'm just going to use that, and that's 0.206 meters. And keeping 3 sig figs here, I get 0.00122 Teslas, which looks a lot nicer as 1.22 millitesla. So I went ahead and did this today using a Hall probe in the physics lab. And one of the complications was that I couldn't control the current precisely, so the current was actually 1.08 amps. And making that adjustment in the calculation up here to 1.08 amps, I get a prediction of 1.32 millitesla. So let's head to the lab and test it out. All right, I've got my coil hooked up to a DC power source, and I'm running this through a multimeter so I can have a more accurate reading of how much current is going on here. And I've hooked up my Hall probe to my software that's going to read out how many Tesla's magnetic field we're looking at. And I'm going to try to place the Hall probe right at the center of this thing. I'm not trying to do this super quantitatively, I'm just trying to eyeball it, and I get 1.22 milliteslas. Okay, so in my somewhat imprecise way of handling this in the lab, where I was just eyeballing the center of the coil, I got 1.22 milliteslas for my experimental value. And when I get a percent error on that, that's about 7.6% error, which is not bad considering how crude the experiment was. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.